Okay, good evening. We're going to take a look at a problem that comes from reaction engineering where we're solving two simultaneous equations, nonlinear, in two unknowns. And we have this reaction system. This isn't exactly like yours, but it's pretty close. So I think you'll get the idea if we solve this one. Anyway, we got A plus 2B goes to C plus 2D, and that's has a K, which is the equilibrium constant of 2. And also, we have A plus C, so the product of the first reaction can react with the reactant of the first reaction to form 2E, and that has an equilibrium constant of 3.2. And so we're going to set this up with, it says to use extent of reaction, so we'll do that. And we have an initial value of 1 mole of A and 3 moles of B. So we'll set up kind of our table like we do in to keep track of reactions. Just makes it a little easier. We'll just put it as A and B. And I guess we just have C, D, and E. And I'm going to give myself a little space here, so I'll move them down just a little bit. And up here, we're going to have E1 and E2, and I'm just going to use E1 and E2 as the extent instead of the squiggle. I think you can put the squiggles in. If you want to get a little more detailed, you can. You could go up and put symbols in, but I'm not gonna do that right now. I'll just use the E's. So then we'll have what's coming in and our change and what's coming out. And those would just be moles. So this is moles. And then we'll have the mole fraction. And so we'll put in the initial values here. And I'll need a little bit even more room. So I'm going to move all. Let's see. Let's just move these E's over here. Yeah, that kind of gets them out of the way. Okay. So we've got 1 mole. Let's see. We have 1 mole of A, so that's coming in. Or initial. You can either think of it as coming in if it's a flow reactor, or the initial, and then the out is the after for a batch reactor. But and then we have 3 moles of B. Nothing for the rest of them. We're gonna guess at these. So these will just be we're just gonna put in values to get us started. Since we have 1 mole, we know that the first one can't be bigger than 1. I'm going to put it as, and this is a 2, so I'm just going to put this as like point, let's try 0.5. And this next one, since this will be quite a bit even less because it can only be react as many moles as C is produced. So let's try 0.2, let's say, for that one. And I'm going to name these cells so they're Control Shift F3, and now we have them named. And now we're going to look at the change here in terms of E1 and E2. So I'm going to go for the change here. It's going to be equal, and the moles of A, since it's as a stoichiometric coefficient, this will be minus because it's reacting, and then minus this guy. Okay. So with those guesses, I'd have 0.5 minus 0.2, and I'm using the extent here. This has a stoichiometric coefficient of -1, because since it's a reaction, and a -1 down here. So then coming out is just going to be equal to what's coming in plus the change. And we get 0.3. And for B, It's just involved in this first reaction, so it's going to be -2 times the first extent. And again, I can probably just drop that down. C is going to be plus. So that's equals the C is formed in the first one, but reacts in the second one. And has stoichiometric coefficients of 1 and -1. So that D here is involved in the first reaction and has a stoichiometric coefficient of 2. So we go 2 times X first extent, and F, or E, is the second one. Okay, and I think we can just add those up, and we'll get the total down here. And it really should be equal to what came in, because I don't think we're changing moles in either one, but just sum them up anyway. So then these will be our mole fractions. And I'll hit this with F4 to kind of lock that in place so I can copy it down and that'll stay the same. And there's our mole fractions. Now, we're going to make these reaction quotients. And the reaction quotient is just the reactants raised to the stoichiometric power divided by the products raised to their stoichiometric power. So, or products over reactants. Sorry, I got that. So it's the product. So it's YC times YD, and that's going to be squared. And that whole quantity, that's the products, divided by the reactants, and we've got YA times YB squared. Okay, so that gives our first one 2, and that's just going to be equal to the second one, which is going to be YE squared divided by YA YC. Okay, and so we have two values. Of course, these aren't correct. There's 2 ways we can go here. Well, there's more than 2 ways, but we could set this equal to these values here, K1 and K2. But I'm just going to take these down. I'm going to put our K1 and K2. Make it a little more general. These should really be big K's, but to distinguish my rate constants, not equilibrium constants. But and we'll just go ahead and name those. And we're going to have our equation 1 that is going to be equal to the reaction quotient minus our K. We want that to be equal to 0. But, let me do that too. I'm going to name these 2. And then we have reaction quotient minus K. And equation 2 is going to be the reaction quotient of 2 minus the K. And I want both of these to be 0. So we're going to change these extent of reactions here until both of those are 0. So I'm going to pull up solver. So up solver comes, that's data solver. And I'll just use the first one, the first equation here, to a value of 0 by changing these two. And I'm going to add the second one as a constraint. So I'm going to add this guy, setting equal to 0. Okay. And I can add other constraints here if I wanted, that the mole fractions can't go out of bounds and be less than 0, but I'll just we're gonna just say solve and hope for the best, and then we'll check these and make sure that no mole fractions go over 1 or less than 0, and that we get kind of what we think we should. So I'm gonna go ahead and hit solve, and it looks like it drove these to near 0. Here's our mole fractions for each one of these. It says over here it found a solution, so I'm going to keep the solver solution. And this looks pretty good to me. I'd have to check these. And this wants a mole percent. So here's my extent of reactions in moles for both of those. And then also this is the mole fractions, and it wants mole percent. So we're well on our way, and we'll check those with the checker and make sure that that works out. But I hope this helps you out. Like I say, your equilibrium problem's a little different than this one, but I think you get the idea. So that's solving basically two equations, two equilibrium equations and two unknowns. They're nonlinear, but really pretty easy with solver most of the time. Sometimes the solver won't find a solution or that, but as long as you give it a good shot, you don't make usually you'll make, when you make errors or stupid errors, you'll subtract instead of add, or those kind of things that can and then your mole fractions, it won't find a solution, or your mole fractions will be crazy or whatever. So if it doesn't work, normally I look for those kind of errors first and make sure that I actually put the equilibrium equations in correctly, and I didn't screw up a minus sign or something like that. And also that these don't go out of bounds, that the guesses are reasonable from what I expect. Or like I said, if I only had 1 mole here, I know that the extent can't be any bigger than 1, and it's going to be significantly less than that. So anyway, I hope that helps, and I will talk to you later.